resuming our discussion on doing level 2 of the hierarchy, which is how do we incorporate doing or action. Based on the questions I got during the break, I just want to alert you that if you look here in this equation, there is no term for x3. So there is the distribution over x1, the distribution over x2 given x1, this guy, and this guy's gone because now I removed its causal mechanism, removed its parents, and then there is x4 and there is x5. That's the whole point, right? That's the difference between this guy and what you will see there. I mean, if you want to think about it intuitively, in this case, the idea was x3 was caused by x1. But now that I'm intervening, I'm saying that x3 is being caused by some external action. It's not by this particular guy. As far as technique, this is what I want you to know about. This is pretty simple. And as I said, in terms of computation, once you have this guy, you can just run a normal inference algorithm on it and you're good. So all of your investment carries once you modify the structure in the right way. What I'm going to show you next is an interesting example that received significant attention in the literature. And it's meant just for exposure of what can you do with this do business. There may be hairy equations, don't worry about this. In fact, I hope you will find the example entertaining, but it will also be making 2 points. Let me see, do I have it? Not yet, okay. It will be making 2 points. One is about what can you do now once you're able to reason with intervention. But it will also bring another methodology for estimating parameters from data, which is different from what we've done in the course so far. Okay, so these are 2 different points. But let me just first say the following about do. There is something called the do calculus, which is a set of 3 rules that allow you to reason about doing as opposed to seeing. So let's look at this expression. Again, I don't expect you to remember these, but I just want you to know that they exist and how they look like. Look at this guy here. What is the property of y given that I do x and observe z and observe w? So there's 2 observed variables and an intervened upon variable. This rule says this is equal to that. Look what happened here. We're dropping z, ignoring an observation. They're equal, assuming you have the following. What is this? You have not seen this notation before. This says y is independent of z given x and w. So it's another way of notating conditional independence. Once more, y is independent of z given x and w. But where? In a graph that has been modified. So look at here, look there, look there. This notation basically tells you take that graph and remove either incoming or outgoing edges to on. So you do some modification to it and then you test independence there. So if this condition holds in your graph, then you can do this. You can equate these. Look what happened in the second rule. What is the property of y? Given that I did x and did z and observed w, what you're doing here is replacing doing by seeing. It's the same. It's saying it's the same. Whether you did it or we observed it under this condition, and then here you're ignoring actions. What is the property of y given that I do x, do z, w, Okay. The point is, just like you have laws of probability that we've seen in chapter 3, right? Bayes' rule and this and that, then you actually have equations or identities that allow you to reason algebraically about interventions. This is basically just last decade or so. It's known as the do calculus. You need to know the word do calculus and that there are 3 rules that have very strong properties. Now we go to the example next. Okay. I will make multiple points about this example. You've probably seen versions of this, right? So this is about whether smoking what causes cancer. So there is this causal structure, cancer, tar level, smoking, and a genotype. Right? We'll see later. The tobacco industry argued that there is probably some genotype that both causes inborns to have craving for nicotine and also cancer. Now, before we get into the do business and show you one application of level 2, I want to make this orthogonal point. Genotype, when it says hidden, that means when I give you data about this problem, there are 4 variables, correct? What that's saying is your data in every example, smoking, tar, and cancer will be observed, but this guy always not observed. So if you draw the table, you can have 4 columns. One of these columns is always question mark, question mark, question mark. In this literature, people, when they do the data set, they don't put that genotype in the data and put question mark. They just don't put it at all. And they will just say in the graph that it's hidden. Now, when we did parameter estimation, I gave you a graph like this, and I gave you data. And the way we approach this problem is how? You learn the parameters of the graph from the data, and you say, here it is. And then you say, okay, now what do you want me to answer? And I answer. So the estimation was query independent. Right? Model, data. I'm not asking what do you want to do with it. Just learn the parameters, and here it is. Now, there is a better approach, which is exercised a lot, and you'll hear as we go on. No, I don't want to do that. I don't want to actually learn the parameters of this guy from the data. Tell me, what is the question you want to ask? What question you want to ask about this model? Typically, people are interested in a specific question. And you say, that's the query I'm interested in. I want to know what is the probability of cancer given that I intervene and ask someone to smoke. That's a query of interest on this graph. I want to know to what extent smoking causes cancer. So the probability of cancer given do S. That's the single query I'm interested in. I don't want to know other things. So what you would do in that case is, you would take that query, that question, and you try to flesh it out and see if you can write it as an equation where all components of that equations can be estimated from the data. And you try to estimate those particular components instead of building. So what you'll see in this example that's coming up is precisely that. Let me show it to you again. Don't be scared by the equations. Okay, you're still scared, but the whole point of this, look, it's innocent, at least what we want to say about it. I'm trying to do this. I'm trying to compute the probability of cancer given we ask someone to smoke. Because I'm trying to see really the impact of smoking on cancer. And I want to see if I can write this in a way so that I can estimate it from data where this guy is hidden. And what this derivation shows you is I can rewrite this like that. 2 points about this example. First, look what I used to get here. Probability axioms that you know, you started in chapter 3, and things that you don't know, like the do calculus, which we just put on the previous slides, right? I'm applying these rules, I got this guy. Now, what's the main point about this guy? You look at it, there is no genotype. Look at the first quantity. Cancer given, tar, and smoking. Probability of smoking, probability of tar given. Okay, now that's a big deal. Why is that a big deal? If I have a data set in which S, T, and C are all observed in every row, and this guy is always hidden, what did I show you? I can estimate this guy from that kind of a data set. Because I can estimate, as far as this expression is concerned, that data set is complete. You guys see that? And I have a unique estimate for this guy. And similarly for these terms. So a problem where the data set is incomplete, and not only that, but it has a variable that's hidden, always missing in everything. When I went for a specific query, not for any query, picked one, I turned it into kind of a complete data problem. This theme is everywhere in this line of work. You guys see what's going on? These three quantities, I can estimate them from that data set using complete data estimation. It's a big deal. And then in that case, people will say, this is estimable. This term is estimable. Are we okay? Because the next example will drill further on this, take you back to the 60s on this. And any questions on this part here? Okay, you don't have to understand the derivation, just that I was able to express this using quantities that are all estimable from data, and then I'm not affected by the fact that this guy is hidden. So in the 60s, that was the first time when smoking was linked to cancer. There was this report from the Surgeon General about smoking causing cancer, and then the idea was that this is the causal model. This claim was made based on associational data between smoking and cancer. And then the tobacco industry came and said, no, it could be this. You have a genotype that causes craving for nicotine and also cancer. And the interesting thing is the data that was used to make this claim, statistically, you can show that it's also compatible with this model. So the data cannot distinguish between this and that. And remember, when we say this is hidden, that you cannot really observe it. In this kind of a model, you have probability of cancer given due same as probability of cancer. That basically smoking does not cause cancer. If you go and force someone to smoke, that does not change the probability of them having cancer. So in this hypothetical combined three example, Yuda has this story. It says, okay, let's say the two sides come together and say, okay, fine, maybe there is a weak link between smoking and cancer, but still it's possible that. So let's put them together, right? So maybe both of you are right. But then I want to actually try to see the extent to which each cause cancer. What's the strength of each link? Due to the genotype versus smoking. And if you do this, then that would be, to answer that question, you want to compute this quantity. What is the probability of cancer given due S, correct? Now, but the question is always, what kind of data do I have? So the data that I have is only on smoking and cancer. I can't observe this. I don't even know what that genotype is. So if you want to think about it in our old terms, you have three variables. Two are always observed and one is always missing. That's the data that I have. Okay. If that's what you have, this is non-estimable in the sense that you cannot rewrite it in terms of quantities that can be estimated from these two guys, as we did in the previous example. But if you have this model where you're talking about the level of tar deposits in the lungs, and you have this, and now you're collecting data on smoke, tar, and cancer, then this is estimable. And we just showed you how in the previous slides. It was actually written in terms of quantities that can be estimated from the data. This is a theme, main theme of this line of work. Many things are happening here. One is this notion, which is orthogonal to all of this, which is when I have a structure and I have data. When we looked about it before, we said, I'm trying to learn the parameters of the model. I have the structure, and I have data, I'm trying to learn the parameters. And we looked at complete, incomplete, and maximum likelihood, and sometimes it's not unique. But we were trying to buy too much. We were trying to quantify the model and prepare ourselves for any kind of query. This is something more specific. It says, no, 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 give me the query. Then I can do something more. And then the question is estimable, not estimable. And at the very end, I hope if we have time, people do fancy things with this beyond this particular one. And the other thing that is happening here is this new type of queries of doing. I hope you appreciate this because, look, in this example, the other way to do this is you can do experiments, right? You cannot go and force people to smoke and see if they're going to develop cancer or not. You can't do that kind of experiment. You got to try to estimate this from data. So this is extremely valuable if you're able to do this estimation from observational data in this particular case. Okay, any question about this? Because I'm going to now move to counterfactuals. Yes. In this case, but in this line of work, there is tons of results on this. On when is it estimable or not, and what kind of criteria the graph has to have. This is just an illustrative example. Yes. Now we'll talk about the step 3 of the ladder, or counterfactuals, and this would be the only left technical thing, and then we'll pop up and say some more general remarks. So we're going to do this through an example. You have this scenario. You have a prisoner that's to be executed. You've got 2 riflemen. You've got a captain that issues the signal, and there's a court order. And in this case, initially we're going to just assume completely functional. It's a circuit, in a sense, that the captain will issue an order to the rifleman if and only if they get the court order. And rifleman A will shoot if and only if they get the signal from the captain. Same thing for B. And the prisoner will die if and only if either of the riflemen. Pretty simple. Okay? Now, the whole point behind this example eventually is we're going to ask a counterfactual question and see how to answer it. But let's just warm up. We can illustrate the main point without getting into probabilities, and then we just add that at the very end. So if rifleman A shot, then the prisoner is dead. That's clear, right, from this model. If the prisoner is alive, then the captain did not signal, correct? You agree with that? And that's an abduction. Now we're going this way. If rifleman A shot, then B shot as well, correct? If A shot, they received the order from this guy, and that means this guy received the order as well, so we also have that. Now we get to business of action. If the captain gave no signal and rifleman A decides to shoot, the prisoner will die. So decides to shoot here now, that's do A. So not C, do A implies dead, right? And B will not shoot. See now a difference between this and the previous scenario. When I told you that I observed that A shot, then we concluded that B shot as well. But in this case, no, this was not an observation. This was a decision by A to shoot that doesn't lead to the same conclusion. And as we discussed before, you know how to do this, correct? What you do is you delete this link. Maybe now, logically, it's a little bit easier. What's the difference? The difference is before I had if and only if between A and C. And then I come and told you A is true. Then you conclude C is true. When you did this, you removed that equivalence. So when I come and tell you A is true, you do not conclude that C is true. That's the essence of it. It's pretty simple, but I showed you with the smoking and cancer example how serious things you can do with it. Now we get to the punchline. Here's the counterfactual question. If the prisoner is dead, he would still be dead if A were not to have shot. You agree? How do you compute that? Remember the mini Turing test? That was similar to the last question. To get to this, what happened? Abduction. If the prisoner is dead. Now, if the prisoner is dead, you conclude that there was a court order, right? And then you want to do this kind of reasoning that this guy did not shoot. This is a different model than that in a sense. That's an alternate reality. However, you would not get this right if you did not carry the conclusion that you had from the first reality or the first scenario to the second one. To do the conclusion that you agreed with, you had to answer a do query while integrating the conclusion that you got from the seeing part. So there's two scenarios, and you can't just do them on the same network, because remember, in this network, what is the value of A? Right. And this is false. They conflict. But I still want to take what I've learned from this and put it in there. if this was a probabilistic model, look what's going to happen. You're going to have some distribution over U, and then what's going to happen from learning this guy? You're going to get a new posterior on that, correct? And it's that new posterior that you have to carry to the new guy. And then when you actually do answer the do query on this guy, you have to use the new posterior to eventually get the counterfactual query. Given that the prisoner is dead, what is the probability that he would be dead if A were not to shoot? That's this kind of one way of notating this particular question. Now, there is a way to do this mechanically, but I'm not going to expect you to know it. I'll just show it to you on the next slide. In fact, it's somewhat similar to what we've done with temporal networks. What people do, there is something called the twin network technique. So what you basically do is you create two versions of the network, and you share some of the things between them. And the idea is it's like two realities. This is the real scenario, and this is the hypothetical one. And then you assert your observations about this. You draw certain conclusions, and then those carry to this. So you can mechanize this, and then throw it into your usual inference algorithm. So I hope you can see that for counterfactuals and for interventions, it's really about modifying your particular model and then running traditional inference algorithms on those modified models. Okay, let me show you one example of where you would use this. This is, I think it's a real case. You're talking about exposure to radiation and causing leukemia, and the causal graph may look like this, that exposure to radiation together with some enabling factors that causes it. There's also a factor, confounding factor, which basically causes both exposure to radiation and leukemia, and so on. So this is the situation. And the classical use of a counterfactual query here is for attribution. Is you have a particular individual that was exposed to radiation and developed leukemia, right? And then you attribute leukemia to radiation. The classical question is this: counterfactual. Given that individual was exposed to radiation and developed leukemia, what is the probability that they would not have leukemia if they were not exposed? And you want that to be greater than half, more probable than not. That's basically a counterfactual query. Now, going back to the same theme that I mentioned before, so computable, new the slides, computable, estimable. The key question is this notion of is it estimable? Because in reality, you have this claim, and then you have data. There are certain things you can observe, certain things you cannot observe. And the question is, can I answer that question? Can I estimate it from data that I have? Can I take something like this and rewrite it in ways where the individual components can be estimated from the data that we have or not? And there's tons of results on that subject. Okay, for those who are philosophically inclined, let me say that this business of counterfactuals is a bit more complex than what we have suggested. Here are two different types of counterfactuals. Again, this is just for people who want to pursue this beyond even what we're doing. People even disagreed on how to interpret certain types of counterfactuals. They've talked about indicative versus subjunctive. Adams is a good book that goes into this in detail if you care. Another interesting distinction for those of you who are philosophically inclined is the following. People have talked about counterfactuals for a long time, but look what they did. Hume and Lewis, philosophers, what they did is they defined causation in terms of counterfactual. So we may define a cause to be an object followed by another, where if the first object had not been, the second never existed. So they defined cause in terms of counterfactual. Same thing for Lewis. A has caused B if B would not have occurred if it were not for A. And what we did here, and what Yuda's work, line of work, and colleagues, was the opposite. You start with a causal model, and then you define counterfactuals on top of that. So that's an interesting distinction, again, for those who are philosophically inclined. Let me also mention now a couple of things. This is from Yuda's upcoming book on the Book of Why. Amusing. You can chase this. The claim here, or the observation, is 10 years ago, 10,000 years ago, humans accounted for 1/10 of 1% of life, and now about 98%. So what happened? And the question is, what computational facility did humans acquire 10,000 years ago that they did not possess before? So in the book, and part of this arguments for counterfactuals, use this figure as imaginary figure as evidence to imagination being a key thing that humans have that distinguish them from other kind of creatures. So the story goes, and again, this is Yuda's upcoming book, about 70,000 years ago, sapiens from East Africa spread into the Arabian Peninsula, and from there they quickly overran the entire Euro-Asian landmass, wiping out the native population. What was the secret? So this guy here is imaginary, half lion, half man. 30 years old, one of the first examples of the ability of a human's mind to imagine things that did not really exist. And here's another quote: "You could never convince a monkey to give you a banana by promising him limitless bananas after death in monkey heaven." The whole theme there is that the ability to imagine scenarios that do not exist, and that's a basis of various things that enable humans to achieve what they managed to achieve. There is two sets of conclusions. There's one here, and then I'm going to say a couple of things, and then another set of conclusions. The point here is that counterfactuals are the building block of scientific thought, free will, and moral behavior. These are Yuda's conclusions, and some places where they have had an impact, and their role in trying to achieve human level intelligence. This perspective that I conveyed in this lecture, and a line of work that's been going for a while, has been summarized by this paper that I alluded to or talked about in the first lecture. It just came out recently, which gives you kind of an index to this line of work on causality through the explication of 7 themes. This was recent. It was given at NIPS last year, and there's an extended set of slides on that link on the very first page. These are the 7 pillars. We touched upon some of them. And what I'm going to do next is just a couple of slides on 2 before, again, I finally conclude. So these are discussed in that paper. It's a short paper, so it's more of a survey and indexes. So people, if you want to follow up any of these themes, you will know where to go by looking at this short paper. So I'll just mention pillar 4, which we already talked about to some extent. This is actually a recent paper, just appeared last few weeks in AAAI by Ilyas, who's actually was also a graduate from Pearl's group. He's currently at Purdue. This paper actually received the honorable mention at this conference, where they use these techniques to talk about fairness and decision making. And here's the classical, or one of the examples that's discussed in this paper, again, for those who may care about these subjects. Same story, you know, you have a model like this, and about hiring that's based on and then data analysis reveals that applicants of faith have a much lower chance of being hired, and applicant sues the company claiming the disparity is either due to direct discrimination, this particular link, or indirect discrimination, which is this particular link, and the company argues the disparity is due to the difference in educational background, that it's actually this thing that's doing it. Then the question is, how do you quantify the length of each one of these links? And again, the constraint here is what can I observe? So you've seen the theme, and there are very recent results, stronger results than before on this that you can chase. Now, one more technical thing before we go to the few more concluding slides. And this is pillar 6, which is missing data, because we talked about this. Again, pretty entertaining, and for you, I can explain this at a high level given what we know. You have a model that has variables z, x, and y, right? This is my data set. Again, in this literature, look, you've never seen this before. Do you see this dotted edge? It goes from z to y. There is no node here, right? This is a shortcut for putting a node there and saying that it is unobserved. So when people put this arc like this, that means there is a common cause for z and y, and it's not observed. What does that mean, not observed? Let's call it w. If you put it here in the data set and call it w, you're going to find a question mark everywhere. So it's kind of redundant to do that. And this is the more common convention to follow it. Okay, we're good so far? Now, the data set has z, x, y, and some w. But now look what's happening. These guys, x, y, and z, have some missing parts. This graph has additional nodes, has r, z, r, x, and rw, and r, y. And what this represents is the missingness of that particular variable. So now I'm adding them to the causal graph. And what does this mean? This means the reason y, or the value of y, causes x to be missing. But I'm not telling you how. I'm just telling you that it is the value of y that is responsible for why x might be missing. And this guy is saying what? That it is the values of x and y which can lead to z to be missing. And what does this say? Y is missing at random. There's really no cause to it. What happened here is I took my original network and augmented it to generate what people call explicating the data missingness mechanism. Why are certain things missing? We've seen that before, right? When we said the test result is missing because maybe people tend not to report negative test results and so on. Okay. Now, look what happens now. If you have this augmented graph where you explicated the data missing mechanism, you can do similar things like before. You come and tell me, I want to estimate this guy. In our book, or without doing this, this data was incomplete, right? Because remember, there's a fourth guy, W, that's missing everywhere. And then I would try to take this and learn the parameters, and there will not be unique ones, and da, da, da. In this case, for this guy, look what happens. You take this, and you manipulate it just using the rules you know, and the independences that are implied by this graph. And you can write this expression like this, as a product of three things, using standard manipulations. And guess what? This guy can be estimated as a complete data problem using a subset of the records in which these guys are not missing. So Rx0 means it's observed, 1 means missing. And this other term can be estimated from those rows and this other term. So the point is, this is actually estimable now, even though you have an incomplete data, but because of the data missing mechanism and the nature of it, it's basically turned into a complete data for a particular query of estimating XYZ. And here's another example, same guy, except this is not missing at random. Now I have this edge, and suddenly it becomes non-estimable. You can no longer do this. Rich subject. This actually happened, this missing data was the subject of a thesis by Kartika Mohan. Some of you may know her. She just finished recently, and she's now currently a postdoc at Berkeley, where they basically end up saying a lot about estimating parameters under incomplete data once you integrate the data missingness mechanism and invoke causality. I think the line here is missing data is causal problem. So they give conditions when you can do this, when you cannot do this, what properties of the graph allow you to do it, and so on. It's pretty interesting. Okay, so I'm gonna these Yuda's conclusions. Remember, all of this is collected from Yuda's slides on this. Couple of final remarks. Model blind approaches to AI impose intrinsic limitations on the cognitive tasks they can perform. To do level 2 and level 3, you need more than distributions, you need models. The 7 tasks described in these pillars exemplify what can be done with models that cannot be done without, regardless of how big the data is. Data science is only as much of a science as it facilitates the interpretation of data, a two-body problem involving both data and reality. This theme where you have this causal graph that makes some claims about the causal mechanism and data together working together to allow you to draw certain conclusions. Okay. I guess the very last line here is human level AI cannot emerge from model blind learning machines. This is the link to this paper that I mentioned, and I think a thank you from Yuda. And these are the folks that worked on these subjects. So that's basically going to be our coverage for the day on causality. I'll see you on Tuesday.